Now, anytime we have a sensor in our mechatronic or our measurement system, and we're trying to measure the value that that sensor is detecting, so maybe it's a pressure, maybe it's a force, and I hook it up maybe directly to an analog to digital converter. So I'm interested in finding out what the value of that sensor is and converting that to some digital thing so that I can manipulate it. Now, there's a lot of problems that we're going to encounter if we just did that. One obvious problem that we can encounter is that the analog signal magnitude can be too small for our ADC to be able to detect. The least significant bit of the ADC might not be large enough to be able to detect a sensor output that might be on the order of millivolts, for example. Another problem can be the substantial amount of noise that exists on that signal coming from the sensor, and maybe that's coupled in somewhere in the wiring, or maybe that has to do with the way the sensor is designed on its own. Another problem might be a DC offset that exists on that signal. I want to get rid of that DC offset because it might push things out of the range, out of that full-scale range of my ADC. My ADC might saturate with that DC offset. Fourth problem might be that I have high output impedance from my sensor, and that really indicates that I could have loading problems with whatever I'm actually interfacing that to, maybe an analog to digital converter. So these are just 4 examples of problems. There are many more that can exist if you try to directly connect a sensor to a digital acquisition system with nothing in between. To solve that problem, we're going to insert another block of circuits and talk about another block of circuits that can exist between the sensor and any kind of digital acquisition that you might have, all related to the general theme of signal conditioning. And so that can include amplification, that can include filtering. All of those things will be relevant to that signal conditioning block. A great component option for solving some of those problems, and something that will be fairly ubiquitous throughout some of these signal conditioning circuits, is the operational amplifier, or as you probably know it, the op-amp. So the op-amp symbol that you've seen before is a triangle, effectively. It's got 2 inputs. We often call those the inverting input, V minus, and the non-inverting input, V plus. It has an output that we often designate V naught, or VO for output. And a really distinguishing feature on the op-amp is 2 additional lines here that are the power supply. So this is a powered component. It's not like a resistor where there's no power supply hooked up to it. An op-amp requires a power supply to be hooked up to it. And in this case, I'm going to use VDD to designate the positive side of my power supply, so maybe plus 5 volts or plus 15 volts. VSS will be the negative side of my power supply. And there are a couple defining features of an op-amp. One of those is a very high input impedance that can help you with problems like loading. So the input impedance on an op-amp is typically going to be greater than about 10 mega ohms, and often far greater than that 10 mega ohms. I'm also typically going to have a very small output impedance. So instead of maybe kiloohms or tens of kiloohms that I might have from my sensor, if I put an op-amp between my sensor and whatever I'm trying to use to measure that sensor, I now have an output impedance that's very small, so more like 100 ohms or even down to single ohms. Right, really the defining feature for what the op-amp is actually doing, right? So the output voltage is going to be defined by the difference between that non-inverting and inverting input multiplied by some gain AV. And AV is typically very high. You're looking at something like 100,000, a million defining that gain. So a very small difference between those 2 inputs are going to still lead to a pretty high output voltage. So another way of thinking about this is looking at this graphically. So if I plot my input on my x-axis here, V plus minus V minus, and my output on the y-axis, I have a really steep line here. And the slope of that is my gain, that AV term, so something very high, like 100,000 or so. A defining feature of a real op-amp as well is that that is going to level off or saturate at some point, and that's going to be the power supply that I use, or something fairly close to that power supply line. So if I had a power of +5 and -5, maybe it would saturate at something like 4 volts and -4 volts. I can also have what are called rail-to-rail op-amps that actually saturate at the power supply. But anyway, the point is I have a very, very high slope here, and then I'll get some saturation in my output. Given those defining parameters of an op-amp, I can actually go in and analyze a very simple op-amp circuit and then back out some general rules that I can use for these op-amp circuits. So in this case, I have an input voltage going into that non-inverting input. So in this case, V plus is equal to V in. And I have my inverting input connected to the output. This is called negative feedback, when I connect my output through anything here to that inverting input. But in this case, that inverting input is connected to V out, so V minus in this case is V out. And if I use that simple equation that defines how an op-amp operates, right? So I have my gain times V plus minus V minus. I can substitute in VI and V naught for those terms right there. And I can ultimately solve for V out in this case. Or V out is going to be V in times the quantity A over 1 plus A, where A is that op-amp gain. And remember, A is really high, so this is something like 1,000,000, right, which is far greater than 1. So this whole term is going to approximate 1, which is basically going to give me V out is approximating this input right here, right? And this particular circuit has a name. This is a unity gain buffer, and that's because I have a case where I now have a very high input impedance because I have an op-amp here, but V out is effectively the same V in. So I'm just changing the kind of input impedance that my sensor might see and the output impedance that my measurement system, my analog to digital converter, my voltmeter, whatever might see. Right? So I can actually change those impedances by using something like a unity gain buffer here. These op-amp parameters ultimately give us some really nice rules for analyzing op-amp circuits. And for the most part, when we're not dealing with a lab or something in the real world, we can assume ideal op-amps. And the first rule of an ideal op-amp is that it has infinite input impedance. And that means that the current going into the inverting and non-inverting inputs is going to be 0. Our second rule for an ideal op-amp circuit is that our inverting input is going to equal our non-inverting input. And that's assuming that your op-amp circuit is in a negative feedback configuration, where you have an impedance between the output and the inverting input. In the example we just saw, there was 0 impedance, right? It was just a wire connecting the output to that inverting input, but I could have some kind of impedance. It could be just resistors. It could be a complex impedance with capacitors or inductors as well. But the point is the output is connected to that inverting input. And if that's the case, then V plus equals V minus. Those two inputs are equal. So those are my two basic rules. To kind of reiterate those graphically, I have my op-amp circuit right here with my non-inverting and my inverting input. Then the currents going in here, I'm assuming infinite input impedance. So I plus and I minus both equal 0. And I also assumed that my number 2 rule, assuming I'm in some kind of negative feedback configuration, so there might be some random block of impedance in here, so some Z shows up right there, but my output is connected to that inverting input through some network of stuff, then in that case, my V plus equals my V minus. So V plus equals V minus here. It's also really important to recognize that even though no current can go into an ideal op amp, I can have currents going in and out of the output of the op amp. And remember, that's because I have that power supply hooked up to the op amp. So I can kind of think of this as a V out in here connected to my output, right? And so that can provide some current to the output, or it can sink some current from the output. That's often a big source of confusion for analyzing op amp circuits, that I have no current going in, but I can have currents coming out.